I got asked this question during a Facebook mock interview and I totally failed. So I decided to dig into it, and after hours, I finally understood the approach. So I'm going to share it with you. First, let's read the problem. Given an M by N board of characters and a listing of strings words, return all words on the board. So we got our board right here. It looks like an array of arrays representing the rows and the individual cells. And then we've got our words, oath, pee, eat, rain. So we're trying to find those here. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once in a word. What does this mean? All right, we take a word, eat. That means it must be constructed of adjacent cells only going left or right, or up or down. So we've got E, A, T. It could also go up, it could go down, but if there was a right here, we can't go from the E to the A. And it also says that the same letter may not be used more than once in a word. So E, A, if this was, let's see, basically I can't go back to the same letter and use it twice within one word, but it looks like we can use it in multiple words. So if it was EAT and ER, we could use that same E. And then we have our second example. Let's go through the first example. So we found eat, and then we have oath, O-A-T-H. Notice that it can wrap around, so it could go horizontally and then vertically. But the other words we can't seem to find. So we have P. There just is no letter P, so we can't possibly find it. Rain, we do have an R right here, but there is no adjacent A. So it looks like we can't find rain. Here we have another board. So we have the word A, B, C, D. We got an A, we got a B. We have a C right here, but it is not horizontal or vertical. So unfortunately, we can't find that word. So that's basically our problem. The first thing I want to do is to understand how a human would go about solving it. Well, that's why I wrote a few examples here. So we have a few words here: cat, cap, rat, apple, and calf. And then we have a board right here. So we got our cat here, we've got an app, we got a tape. And we want to go through this board and see how would we approach finding all these words. All right, so first we've got cat, C-A-T. Great, we found it. Then we look for cap, C-A-P. So what did we do right here? Well, first we went to the right, Here, we went to the right, and then we went down. So why did we go down? Well, it seems pretty obvious as a human, but what if we were a computer? Well, the first thing we do is methodically go to the right. Then we methodically go again to the right. So we kind of exhausted our possibilities. But we should be able to go in all directions. So we go to the right, we exhausted that, then we backtrack and say, okay, so we found cat, but what other words can we find which start with CA? Well, it looks like we could find cap. So we already exhausted that right direction. What if we go down? All right, P, great. We found cap. But really we could go in any of the 4 directions. So starting from C, we could have gone to the left. Well, not really, because that's the end of the board. We could have gone up, not really, because it's also the end of the board. We went right, which is what we did. We also could have gone down. So what happens if we would have gone down? We also found an A. And if we kept going down, we also found a T. So we actually found the word cat 2 times. And that's okay. We just need to deduplicate it. So next, what if we went down that same rabbit hole of going down? We found A. There's no P here, but there is a P here. So essentially, the idea is, as a computer, we want to keep checking all 4 directions, then backtracking, seeing if there's any other word that we can find on that backtrack, and finally going back to our first letter. Well, okay, so what if we want to find words that do not start with CA, like rat? Well, as a human, I would start looking for an R, and there is no R, so we give up. So then we look for apple. Okay, we found an A, awesome. We look in left, nope, right, nope, up, down, we found the P, awesome. So from the P, we go left, no, A, we already visited, so we can't go there. To the right, yep, we found an app. But now we're looking for an L. We can't go to the left because we visited it. We could go up, but that's not it. Can't go to the right, out of bounds. There's no L. So it looks like we have to give up on that. But there's another A. A, P, P. Oh, looks like we have to give up on that. And then we have calf. So here we also start with a CA. We found the T, but there's no H, so we give up on that. All right, so that's basically the algorithm for finding the words. How do we code this? Well, we try to remember all of these different steps that we took as a human and codify it. The first thing that I did was I tried to find words that start with the same letters. So cat, cap, and calf, they seem to start with the same letter. So instead of trying to go through each one of these and repeating so many steps, we could just sort these into similar letters. Well, we have this structure called a tree. It's spelled T-R-I-E, and it helps us do exactly that. This is what a tree looks like. So we have the root of the tree, and then we go down our list of words and we try to see what letters do they have in common. So cat, all right, starts with a C, great. A, all right. Root. Is there a C? There is a C. Okay, so A is going to become a child. T, C, A, T. That becomes a child. And then we use this character right here to signify that it's the end of the word. You might be asking yourself, why don't we just say, all right, C-A-T, and then true for that last T? Well, it's because we have this scenario where it could potentially be another word that starts with cat, calf. This is a little difficult to visualize in your head, so let's make a JavaScript tree. So we have our C, we have our A, we have our T. end of the word. But we also have cath, we have our C, we have our A, T, H, end of the word. And then we have cap, C, A, now it branches at the same level as the T. And we have the P, C, A, P, end of the word. Yeah, that's basically how it looks. And if we wanted to add the other words, it would be pretty similar, R, A, T. They have no common start, but we would have to go through all of these different words. All right. So now that we know what a tree is, how do you actually construct a tree? Well, I made a function for that. We start out with an empty hash map. Then we go through all our words one by one, and we say, okay, what's the current node? We start with the root. There's the root. And we do exactly what we just did. We say the current node is the root. And then we split up the letters, since it's a string, into an array. And we go through each letter. And we say, okay, does the current node contain that first letter? So the current node is the root. Does it contain a C? Right now it does not. When we first started out, it's just an empty hash map. So we say, okay, if it does contain that C, then we move the current node to that node. So if C already existed, now C is the next node instead of root. But if it doesn't exist, then we create that C. And that is done by creating an empty hash map on current node, which is root C. And then we just keep going, and current node just keeps increasing. And as soon as we get to the end of the letters, we want to say, okay, end of the word. We use this end of the word character hash map. It's just arbitrary character, and we say it's true. So that's our hash. It says true. That means CAT, that's a valid word. CATH, that's a valid word. CAP, that's a valid word. Great. So we created our tree. At the end of the for loop for the word, we just go back and the current node becomes the tree. Awesome. So now that we have our tree, we can efficiently traverse our grid. So what did we say we need to do? Well, first of all, let's start out with the return. So how we usually do a recursion is we keep the results in a variable, and then we just append the results to that variable. Remember, we said that we do not want any duplicate results. Well, that's why we create a set where element can only appear once. The only thing is we need to convert it back to an array at the end so that LeetCode properly reads it. And then we have the current word path. So as we're going into this recursion, we want to keep track of what is the word so far so that we can append it into that found words set. And then we also said that we have to iterate through each individual cell, because just because one word is found here, O-A-T-H, the next word, which is P, might not even be here on the O. In fact, it's not anywhere. We have to search through every single cell in the grid. So this is an n squared, but kind of have to do it. So finally, we have the DFS function, which is the depth first search. And it takes quite a lot of variables here, arguments. We have the board, which is the representation of this board, array. Over here, the for loop is actually going through each row and each cell, ij, and we pass that ij here. We pass that nice tree that we created, and then we have the found words, which is the result, and we have the current word path where we're going to build the word every time that we recurse. And every time that we finish a recursion, it's going to backtrack, and the word is going to go back to one character less. All right, so we built our tree, great. Then we have our DFS function finally. The first thing we want to check is, did we reach the end of the word? So the current node, if it contains the hash symbol, that means that we reached the end of the node. The end of the word. And if we did reach the end of the word, then we push that current word path. So how does this work? All right, we went through the tree, C, A, T. Right now in the code, we're at that T node, and we check, is there a hash symbol? There is a hash symbol, so we just reached the end of that node, and so far the word is CAT. Great, so we push that. But why don't we return? Because we also have cath. So we already did cat, but we also want to go through cath. Okay, we'll handle that later. So if we reach CAT, that means we found all those letters in the grid adjacently. We don't really need to check any adjacent cells because that's it, it's the end. But if we found cat, and then we also want to find cath, then we do need to check around. What we first want to make sure is the cell that we're going to check is going to be in bounds. So if we reached n and then we're checking to the right, so row I is going to be 0, col I is going to be 0, 1, 2, 3, 4. So 4 is out of bounds for that row. I have this check boundary function right here. Pretty straightforward, takes the row, takes the cell, checks the board. If row I is going to be less than 0, so it's somewhere on top here, or it's going to be outside of this bottom row, or the column is to the left, or the column is to the right, then it's invalid. So those are our 4 checks. Let's go back to here. Okay, so then we have the cell value. So if it is in bounds, so we found A is indeed in bounds, then first we want to check whether we already visited this character. Why? Okay, so say we went to O, and then we went to A because that's our first direction, right? What if we technically could go back to the left, right? Because we want to check all the directions. So O, A, O, A, O, A, we're now stuck in an infinite loop. And that's why we have to mark the cells that we visited with a dash. And at the end of the recursion, we want to unmark it, because as soon as we go back, that is a valid path again. And basically, it's scoped just to that level of the recursion. All right. So yeah, we make sure that we do not backtrack here. What is the next node? So we're at O. We're checking the value to the right. It's A. Great. and that becomes our next node. So in this example C, we check the to the right, which is going to be A, and A is our new node in the tree. So we just went to the right, A, C, A, that is the new node. Great. And if that node does not exist, so what does that mean? That node, sorry. Yeah. The next node, we're actually checking whether it exists in the tree. So the cell value, we just went to the right. Sorry, getting all of this organized. We went to the right, CA, that's the one we're checking. Does it exist on the tree? C was the previous node. Does A exist? It does. But if we were checking for like CB, that does not exist on C. Or like say we're at T and we're checking for P. Well, T doesn't even exist on this tree, so there is no next node. And this works for root as well. So if we were checking for rat, it's the other way around. So we're checking on the board. So E, I don't think anything starts with E. So the node right now is root. We're checking for E. E just plainly does not exist in this tree. So we just move on to the next cell without having to check all of these different words, which is why we want to use that tree. Okay then, so the next part is if we did in fact find that next node, then we append the cell value to the current word path, and then we could keep recursing. So we have the board, row I, column I. We mark it as visited to make sure that we don't accidentally go back to it. And then we have our 4 recursions in the 4 directions. So the next time that it recurses, let's say we have the full word oath. If we have the full word oath, then our current node is going to be T right here. So the next, it will contain the hash, meaning as soon as we land it, even if we're out of bounds, that's okay, because we already reached the end of the word, and this is the check which says, okay, we're at the end of the board. If we go right on N, then it's going to fail the boundary check next time around. And if we hit a letter that doesn't exist in the tree, then we return here. And if we already visited the cell, so we go OA, we go back to left, we do not keep recursing. So how do we represent the directions? We have row +1, that goes down, row I -1, that goes up, column I +1, that goes right, column I -1, that goes left. And let's not forget to reset our value from the visited cell so that yeah, we can keep recursing properly. Yeah, so that is essentially it. Yeah, this is a little visualization of how the movement goes. So the square brackets are visited, so we start with a C, then we go to the A, then we go to the P. These are the ones that we visited, so CAP. Then we're searching for cat, same thing, CAT. Yeah, okay. That is basically how it works. Let me know if this makes sense. Yeah.